black. Pick one.
So I did get emailed a couple of questions, so we'll look at those today.
I'm gonna write this down.
The questions are from 3.4, numbers 5 and 6. So the first question, what is the cardinality of the power set of Earth, Moon, Sun? List the elements of this power set to answer this question. So we did this one in class, but we used the letters A, B, and C. So instead of just telling you the number, I'm going to tell you to look in your notes, okay? Because you have this in your notes from the last class when we did the power set of A, B, and C together. So you can see how many elements there were in there, all right? You made all the sets that you could out of the letters A, B, and C, including the empty set and the set with all of them. And then for number 6 was in our notes too, but really in a different way. So number 6 reads, all in the family, a family of 4 tries to eat dinner together as much as possible. On Tuesday, some family members sit down for dinner. How many different possible groups of diners are they? So this is actually the power set that we did the very first part of class where you have 4 suits. So we made all the subsets of the 4 suits that we could. So we had diamonds, hearts, clubs, spades, and we made all the possible sets we could out of that, including the empty set. And this question is a little confusing because you're like, well, why would you include the empty set? Nobody's there then. So do include the empty set, and it's just the same number of elements that were in the power set we made of the 4 suits. So that's in your notes too, very first problem. Any other questions to go over?
You don't have it?
Before we leave set theory, I have here application. So this is math appreciation, and similar to art appreciation, what we're doing is looking at different aspects in the area in mathematics that you maybe hadn't thought about or didn't come across in your normal everyday life. But often in math, people ask, what is it useful for? I don't know that people ask that in art appreciation, but they do in math. So here's an example of where set theory, which we looked at in chapter 3, where set theory would be useful. The value of set theory to most mathematicians is not in any particular theorem, but in the language it gives us. Nowadays, even computer scientists describe their basic concept, Turing machines, in the language of set theory. And the author of this, Q-Chu Yan, also goes on and describes some other applications of using the language of set theory. I have another article I thought was very interesting because it uses an area of set theory we looked at in one of your Wiley Plus problems. So this article, thank you. This article is called A Glimpse of Infinity in the Swirling of Light, and you can access this online. And it's very easy to read, very accessible, not too hard. So where's the part that I wanted to show you in here? There we go. So the author is looking at set theory as an application of light, looking at optics. In particular, looking at light, you can see light as a wave. It has properties of waves and properties of particles. So the author writes, infinite mathematics can be realized in optical systems possessing swirling vortices of light. In particular, both demonstrations showed how particular systems mimic exactly a paradoxical thought experiment known as Hilbert's Hotel. And you did Hilbert's Hotel in one of your Wiley Plus homework problems, in which the occupancy of a hotel consisting of an infinite number of rooms shows very strange behavior. These examples seem to be the first ever showing that infinite mathematics not only manifests in some real-world systems, but is essential in explaining them. There's some great pictures of Hilbert's Hotel. Remember you had this problem on Wiley Plus. There's a hotel with an infinite number of rooms labeled 1, 2, 3, 4, and so on, and someone shows up and says, but I had a reservation, and you have to figure out where to put them, and of course the solution is to move all of the people down one room. So this is some easy to read articles. If you get a chance to look this one up, I think it's really interesting. Okay, we are going on to chapter 4. If you haven't really been interested in chapters 2 and 3, chapter 4 is very different, and it might be more to your taste. So hopefully chapter 4 will be something you enjoy. It's geometry. Not like you did it in high school, though. The 4.1, we have the opening question. A baseball diamond is really a square measuring 90 feet on a side. How far does a catcher have to throw the ball to get it from home plate to second base? So let's go ahead and answer this question in 4.1. Let's draw a square measuring 90 feet on a side. That's a baseball diamond. So I'll put little squares to show that this is a square. And then we want to get, well, it's 90 feet on the side. I could put that, 90 feet. And then we're interested in how far does the catcher have to throw the ball to get it from home plate to second base. So from home plate to second base, we're going right across here. And that's the distance we're interested in. So who knows? What can we do to figure out what that distance is? Anyone remember your geometry? Yes? It is the Pythagorean theorem. Good. In fact, that's the title of this section. The Pythagorean theorem. So who remembers what the Pythagorean theorem says?
A squared plus b squared equals c squared.
Good. A squared plus b squared equals c squared in a right triangle. In a right triangle, a squared plus b squared equals c squared. And this is one of the cases where a mathematician would use a double-pointed arrow to mean if and only if. So in other words, if you have a triangle where a squared plus b squared is c squared, then it's a right triangle. Or the other way around, if you have a right triangle, then the lengths of sides a squared plus b squared equals c squared. So the main thing when you're using the Pythagorean theorem to be careful of is the C must be the hypotenuse. The C must be the hypotenuse. So that's the side that's not making the corner, the square corner. Okay, so C has to be the side that's across from the corner. The two sides that make the right angle are called A and B, and the right angle is indicated with a little square that makes that 90 degrees. So A and B you can switch back and forth, but you have to have C be the hypotenuse. So let's go ahead and use that now to find the missing side here. So in our triangle that we created by cutting the square down the middle, we have the right angle formed by the two sides that are 90. So those are our A and our B. And the other side does not make the right angle, that's D. Don't forget the squaring. I don't know why some students forget the squaring, but don't forget it. And then I'm going to take up my calculator and find 90 squared plus 90 squared. $90 squared is 8,100. So I have 16,200 for 90 squared plus 90 squared. And then we'll go ahead and take the square root of both sides. So remember, whatever you do to one side of the equation, do to the other. So we take the square root of both sides of the equation. We have 127.28. Now I'm going to round there, okay? So I'm rounding to the second decimal place, and the third decimal place is a 9. So I make the second decimal place go up 1. And that's just saying I'm closer to 0.28 than to 0.27. In a science class, you can talk about significant digits and how much to round to. In our class, if you're not sure, just round to hundredths places. 2 decimal places. So the topic in this section is the Pythagorean theorem, and we're going to have 2 tasks with the Pythagorean theorem. One is to make sure you know how to use the Pythagorean theorem, and the other task is to prove the Pythagorean theorem. So first let's look at why is the Pythagorean theorem important. There's plenty of facts that people have found out over the centuries that are lost to us because they were not important. Why did the Pythagorean theorem linger? What is important about it? Anybody have any ideas? Well, if you look around the classroom, you see some nice square walls, right? One way we use the Pythagorean theorem is to get those nice square corners. My husband remodels. That's how he spends his life. He remodels. He buys houses and he either fixes them up to resell or he rents them out. Boy, this is terrible. He's a better builder than I am a drawer. So that's supposed to be 2 2x4s put together. And one of the things he'll use is the Pythagorean theorem to make a nice square corner. You can then mark off 3 feet on one 2x4, 4 feet on the other 2x4, and just put one little tacky nail there, because then you can still bend it a little bit. And then you can take a tape measure and measure off 5 feet. So you can pull the wood a little tighter, a little further apart until it's perfectly 5 feet to the 3 foot and 4 foot marks, and then put in some more nails to hold it sturdy. And then you have a perfect right corner. That's if your wood is square, okay? Don't start out with wavy wood. That doesn't work good. All right. Because 3, 4, 5 is a Pythagorean triple. 3 squared plus 4 squared equals 5 squared. And you can do that with larger numbers too. If you make this span longer, then you're more precise. So you can just multiply that by 10. Okay, and because you see the simpler one, the 3 squared plus 4 squared is 5 squared. That's just saying 9 plus 16 is 25. People who like number theory like to look for Pythagorean triples like 3, 4, 5. I've had classes where other students have known some Pythagorean triples. Does anybody know some Pythagorean triples? I have a couple more written down. Let's see where they are here. So these are just integers that fit the Pythagorean theorem. So there's 5, 12, 13, 8, 15, 17. Okay, those are some examples of Pythagorean triples. And like I said, some people who like numbers and number theory would be pursuing finding other Pythagorean triples that were not multiples. It's easy to find a multiple once you have one, but to find a Pythagorean triple that's not a multiple of a known Pythagorean triple, now that's not easy. So let's go ahead and look at our first task. Let's take a look at finding some missing sides. Make sure you know how to do that. So I'm going to write find x My husband sent me a text the other day. He's like, "Dear mathematician, quit asking us to find your x. It's gone and we don't care why." Anyway. So we're going to use the Pythagorean theorem. So when you see you have a square corner like that, that means you can use the Pythagorean theorem. So you'd write the a squared plus b squared equals c squared. And the important thing again is to find c. So which one is c? Which one? 7. Good. Okay. So 7 is not making the right corner. The 4 and the x are. So 7's the hypotenuse. The a and the b can be 4 and x, or x and 4. It doesn't matter which order you put those. So we have 4 squared plus x squared equals 7 squared. 4 times 4 is 16. 7 times 7 is 49. And this is one where we have to get the x by itself. So we'll subtract 16 from both sides of the equation. So the next thing to do is take the square root of both sides of the equation. And then we have plain x. So let's find the square root of 33. Okay, so 5.74. This time the third digit is a 4, so I don't round the hundredth place up. Does anyone have questions on that one? Let's try reorienting the triangle a bit. So it's still a right triangle. There's still a corner there. Okay, this is like your 3x5 card. In fact, if you have a ruler and you use the 3x5 card to make your right triangles, then you can go ahead and measure the last side to find what x is. So we have a squared plus b squared equals c squared. What is the c on this one? 3, 4, 3, 5, or x? X, good. Okay, so the 3 and the 5 make up the right corner, so they're the a and the b. 3 squared plus 5 squared equals x squared. 3 times 3 is 9. 5 times 5 is 25. 9 plus 25 is 34. So the 34 is the x squared. And now we can go ahead and take the square root of both sides. So we have 5.83. Wait a minute. I just gave you a Pythagorean triple, 3, 4, 5. How come if the Pythagorean triple is 3, 4, 5, why didn't I get a 4? Why is that? Okay, good. Okay. So here the 5 is the hypotenuse, good, because it's the longest side. And here the 5 was not the hypotenuse. So be careful there. It's very important you get the hypotenuse where it belongs. Well, I do want to make sure everybody knows how to do this. So this time I'm going to give you one and ask you to work it out, and then walk around and see how it's going for you, okay? So we have 4 feet for one side, x for one side, and 6 feet for one side. Can you please find the value for x? And if you get stuck, raise your hand. Otherwise, just keep working.
Where are you at? Yeah. Did a lot quicker. Sorry, I'm taking time.
So the right corner there?
I hate the freaking Pythagorean, but so many times I hate it. Yeah, I was getting a D in my geometry class, and then I finally did good and got. It was the proofs. Okay, I gotta figure out where the fuck this triangle thing is. It's pissing me off. Do you want help?
Pretty good.
Looking for a triangle? Yep. There should be a right triangle. Yeah, stuck. No. I've got circles. I have a clock. I don't have a clock. You have a clock? No. I got nothing. These are all the duplicative ones. I know there's a red triangle on here because I did it before. Say hello. These? Those aren't right. Not either. What the hell? Okay, now they need to go back on.
Okay, so we have the corner kind of working like your plus sign, okay, to stick these two together that make up the corner. So the 4 squared plus the x squared have to go together, and the 6 is the hypotenuse because it's not part of the square corner. So 16 plus x squared is 36, and let's subtract, subtract 16 from both sides. X squared then is 20, and the square root of both sides gives us x. 4.47. Our units are in feet, so you could say that's 4.47 feet.
What if we got the right numbers, but we put the numbers? What if we got the right numbers, but we put them in the wrong spot?
So I'll put an or. If you put x squared plus 4 squared is 6 squared, that's okay too.
Okay.
Yeah, so that's okay. As long as the 6 is by itself, the x and the 4 can be switched around. Good question. Any other questions? So that's our first task in this section, to be able to use the Pythagorean theorem. The second task is to prove the Pythagorean theorem. Remember, our proofs are irrefutable, unassailable, irrefutable steps leading to an unassailable conclusion. Now, sometimes people get confused what a proof is. So on the quiz, I asked you to prove the square root of 3 is irrational, or some of you had a different root. And some of you said the square root of 3 is irrational because, and then they'd write this out. The square root of 3 equals .732050808, and then they put dot dot dot, and then they'd say because its decimal expansion goes on forever without repeating. So if someone put that proof down, they didn't get any points, which was sad. Does anybody know what's wrong with this? I mean, is this true? Does the square root of 3's decimal expansion go on forever without repeating? Is that true? Yeah, that is true. Why isn't that a proof?
Because a proof is step by step and it has to be able to be repeated.
It has to be able to repeat it, and it has to be step by step. That's what a proof needs to do. That is how a proof works. And this particular proof doesn't show me that it goes on forever, does it? Right? If they wrote out 100 decimal places, it wouldn't show me that the decimal expansion goes on forever. If the student wrote out 1,000 decimal places, it wouldn't show me that the expansion goes on forever without repeating. This isn't a proof because there's no way to show it. There's no way to show the decimal expansion going on forever. The ... is you telling me it is, but the reason you know that it does is a result of the proof. You know it goes on forever because you know it's irrational, not the other way around. You don't know it goes on forever and hence you know it's irrational. You don't know it goes on forever because you can't see it going on forever. You can't know that after 1,000 decimal places it doesn't begin to repeat itself, or after 1,000,000 decimal places it doesn't begin to repeat itself. So this is in fact a result, not the proof. It's the result of the square root of 3 being irrational. So we're going to be careful with our proofs today and make sure everybody gets a hold of a good understanding of a proof. Now there's lots of proofs for the Pythagorean theorem. The life lesson today is to experience ideas in as many ways as possible. So we're going to look at lots of proofs, in fact 3. As we're doing these proofs, we're going to have a squareds and b squareds and c squareds. The Pythagoreans would have thought of a squared as a square sides a by a. Okay, we've had geometry for eons longer than we've had algebra. So when they said a squared, they would have meant a square, a by a. Just like on the floor, you have 12-inch tiles. So how many square inches is that then? Good, 144 square inches. And that actually means there's literally 144 inch by inch squares that you can fill in there on the floor tile. So the square inches mean squares an inch by inch. A squared means a square a by a. So when the Pythagoreans were saying a squared plus b squared equals c squared, they meant that there's a larger square, c by c, whose area is equivalent to 2 smaller squares, a by a and b by b, that are added together for a right triangle. So they sometimes would show the proof like this, with the c squared over here showing that it's c by c, and then the a squared and the b squared being squares off the legs. And they would mean that if you add up the area in these 2 squares, it's equivalent to the area in that square exactly. So that's what we're trying to prove. We're looking at area proofs because that's how the Pythagoreans would have seen it, and that's how most of the Pythagorean proofs are. There's many of these proofs because the Pythagorean theorem's been around so long. Does anybody know a president of the United States who has his own proof of the Pythagorean theorem? Which president do you think was mathy? Which of you knows history enough to know which president would have been interested in math? That would be a good guess, but it turned out to be James Garfield. All right, how about this one? There's an artist who loved math and has his own proof as well. So the artist would come home from a long day of painting and relax by doing some mathematics. What artist would that have been?
Van Gogh. So I want to say Picasso.
Not Picasso, not Van Gogh. Those are good guesses. Lots of squares with Picasso too. Yes?
Michelangelo.
I'm not sure if that's the same name that he used. What was it?
Leonardo da Vinci?
Leonardo da Vinci. I think he might have had that in his name though, but Leonardo da Vinci is the one that I'm thinking of. Yep. So he had his own proof. His proof is really quite involved. It has a lot of movement. It's very beautiful and very hard to learn. So we're not going to learn his proof. We're going to learn some other proofs. So here's where we'll need our templates. There's a scissor going around if you didn't cut your template out. If you need a scissors, raise your hand if you need a scissors. Okay, all right. So you were supposed to cut out the template. It's basically 2 3x5 cards. I have 2 templates here. The point of using these templates instead of a particular triangle is that our proof needs to be true for any right triangle. So these are only shaped out of 3x5 cards because it's easy to take a 3x5 card and cut it on the diagonal. As you were doing that, did anybody figure out the dimensions of the square, where the square's length came from? Did any of you figure that out? Okay, so the square's length comes from the length of the longer leg minus the length of the shorter leg. So if you put that together, you see the length of the long leg minus the length of the short leg gives you the length of the side of the square. So I have a couple of templates because I wanted to show you that these proofs work for any right triangles as long as you have that situation going on. So I have here another template, and here's the length of the long leg, and here's the length of the short leg, and I have the square that has a side, the difference between those 2 lengths. So if we have time, I'll show you the similar proofs with these right triangles that are not proportioned the same as the ones that you're using. So let's start by labeling your templates. Okay. So your long side of your triangles, let's call A, just so we're all talking about the same lengths here. So let's call the long sides of your right triangles A, the long leg of your right triangles A, the short leg B, and then the hypotenuse C. So put A's on the long legs, B's on the short legs, C's on the hypotenuse, and then this square turns out to have a length on its side of A minus B. So you can label that on there, okay? Okay, so once you have that figured out, let's go ahead and get a piece of graph paper. Now, the graph paper is convenient because it matches up sizes for us. If you did not bring any graph paper today, please take a piece of paper and make your own ruler. You will use this throughout the class if you don't ever get a ruler or graph paper. It's not as good, but it's better than nothing, okay? So make up one of your pieces of note paper to be a ruler, and then you can measure, like, okay, now I have 7 lines across and 7 lines tall. Well, you can count 7 lines tall, but 7 lines across would have been harder to make. And if you don't have a ruler, then you can use your ID for a straight edge. That works pretty good. So, graph paper. Where's my graph paper? Here we go. We're going to look at 3 proofs. You only need to make sure you know one really well, but we'll be looking at all 3 because I found that students do better with different ones depending on the student. So we'll look at all 3 and write all 3 down, and hopefully one really resonates with you, and that's the one you'll use. First off, we're going to look for a c squared. So let's make a square c by c. And we can do that by outlining square c by c with our triangles. So I can see that the lengths of each side of this shape are C, but how do I know it's a square? How do I know these corners are 90 degrees? I mean, it looks square, but again, looking square is not enough. We need to prove it's square. What do you know about angles? How many degrees make up the angles in one triangle when you add up all the angles together? Go ahead, 180. Okay, so 180. So on this red triangle, these two smaller angles, how many degrees are in those altogether?
90.
Go ahead, 90. Because we have 180 for the whole triangle, and we used up 90 down here. Well, all four of these triangles are the same, and so these two triangles making up 90 degrees are the same as these two angles. These two angles making up 90 degrees are the same as these two angles right here. So these two angles together make 90 degrees. What about a straight line? How many degrees are in a straight line here? 180, right. So if we take out 90 from 180, we still have 90 right here. So that's how we know we have a square. Next thing to do is to draw this. So we have this shape on with our cutouts, but you can't very well hand that in on a quiz. By the way, you will have to know one of these proofs for a quiz. So let's see if we can transfer this drawing to the graph paper. I'm going to draw a square 7 by 7, and I'm going to make my triangles be 3 on the short side B and 4 on the long side A. You could use any dimension. So I'm saying 7 squares across here, 3 for the side B and 4 for the side A. And you could do that with your lined paper if you're using lined paper for a ruler instead of graph paper. So I'm making a square 7 units by 7 units. So once you have your square sketched out, then you can mark the 3 units where B and A are connecting. Side B meets side A here. And then you can use your straight edge to mark those off. So it doesn't have to be 7 units square. It just is a convenient way to make us all match, so we're all discussing the same thing. Okay, so we've sketched a square and we have the triangles drawn in. Now we have to show who's ever looking at this proof that these are all the same triangles. So we have to label the A, B, and C on all of the correct edges. So again, we're using A for the long leg and B for the short leg. And C for the hypotenuse. And that gives us our C squared in the middle. Well, almost. You do need to show these are right triangles, so put some right triangle corners to show they're right triangles. Okay. So your proof is for any right triangles as long as all 4 right triangles match, and that's why we call them A, B, C and don't label them with 3, 4, 5 or whatever the measurements are, because we want this to be true for any 4 equal right triangles. So that's our first shape that we need for this proof. We need another shape. The next shape, we have to come up with an a squared and a b squared. Okay, we have a square c by c, but now we need a square that's a squared and a square that's b squared. To get to that point, we're going to put our 4 right triangles in this shape. So we have our 2 rectangles formed by 4 right triangles, but there's 2 squares there as well. So there's some empty space that makes squares. So there's empty space here. What shape is that? What is the dimension of that square outlined by the ruler and the pen and the rectangles? How wide across is it and how tall is it? How wide is this? You see 5 inches. Yep. Or A. Yep. So we're going to use the A instead of the 5 inches because we want this to stand for any triangle ABC. So this is going to be A wide. And how tall is it? A. Yeah. So that's why one reason we put the little A's on. So we know it's A wide and A tall. So this is an A squared right here. How about the square up at the top? Yep. B squared. Yep, it's B wide and B tall. So there's a B squared there. So let's go ahead and draw this drawing up above. So again, we can use the same dimensions so that it looks kind of nice. So 3 for the short leg and 4 for the long leg. So again, a square 7 across and 7 down. So we'll get a square that's going to be a drawing of what we have below with cutouts. So we have these rectangles that are, like you said, 3 by 5, only in this case on our little squares I'm drawing them 4 wide and 3 tall. I think I just got in the habit of that. I should think about doing a 3 by 5. But maybe this is good because that way you're remembering as long as there are any right triangles that all 4 match, it doesn't matter what their dimensions are. So we have the right triangles in the upper right here, and the right triangles in the bottom left together forming those rectangles. And we want to identify this as the same rectangles that we're using on the other drawing, so we put the A, B's, and C's on again. So the A's on the long legs, and the B's on the short legs, and the C's on the diagonals. And then the right angles to show that we're using right triangles. And then with the nice A, B's, and C's, it's easier to see that you have a square A tall and A wide. So that's A squared. b tall, and b wide, b squared. So this proof begins with two drawings that we have, both of them made out of 4 right triangles and then some empty space making up squares. C squared over here, a squared and b squared over there. Now what can you notice about these two triangles? I mean, did I just say triangles? What what do you notice about these two squares? They do. They are the same size. They're equal. Okay, so they're equal in size. And for our reader, we can make that real clear by writing they are the same size. Okay, in fact, the size that they are, these are squares now, so there's something squared. The distance across the top is a plus b. The distance tall is a plus b. A plus b squared. And over here again, the distance across is an a across and a b across, and the distance tall, a plus b tall. Whatever a and b are, when you add them up, you get the height and the width. So these are squares, a plus b squared. So now we'll just describe why that matters. And why that matters is over here, this square is made up of the big empty c squared plus the 4 right triangles. Whereas the other square, which is the same size, that's made up of the empty a squared and b squared plus the 4 right triangles. Now we have to let our readers know that these 4 right triangles are the same size. Does anybody remember the area formula for a triangle?
Base times height.
Almost.
Times height.
What is it?
Half base times height.
Half times base times height. Yep. A half times base times height. So all of these right triangles are 1/2 times a times b. So let's just write that in. We have the c squared plus 4 times 1/2 times a times b. And over here you have the a squared and the b squared. And 4 times 1/2 times a times b. So we have these two areas that are the same size. They're the same size squares. The one square is made up of c squared and 4 times 1/2 times a times b. And the other square is made up of a squared and b squared plus 4 times 1/2 times a times b. So if you take away the 4 triangles, since they're equal, you can take them away, right? They're the same. These triangles are the same. So if I subtract them from both sides, I get the Pythagorean theorem. We start with two areas that are exactly the same size. We take 4 right triangles away from both areas, and what you're left with are two squares over here, a squared and b squared, and 1 square over here that have to be the same size, because we started out the same size and we took away the same size area. So this is the first proof, just through here, okay? And you do need all of it. You need the 2 drawings and the algebra to describe what the drawings are saying. We're going to look at 2 more proofs on Friday, and then hopefully one of those will click. One of the 3 will hopefully resonate with you, and you'll be like, okay, that one I can remember for the quiz. So I'll see you on Friday. If you have any questions, see me after class.
We didn't do the class activity today, did we?
Nope, class activity is coming up on Friday, and you do need these templates for that. The class activity calls for these templates, so cut yours out if you haven't yet, okay? I'll see you on Friday.